Hi, and welcome to Lesson 1.3, Other Types of Geometry. So we are mainly going to look at two other types of geometry in this lesson. There are many other types of geometries outside of just these two, but these are two common types that sometimes show up outside of our Euclidean geometries. So we've already looked at the idea of Euclidean synthetic geometry, which is our typical geometry that we always use, where we draw lines and put dots as points. And then we also had a look at Euclidean coordinate geometry, which involves coordinates or ordered pairs, and we can use a coordinate plane. Those are our two most common types that we'll use this school year and we'll explore. These next two are, again, like I said, some other common types of geometry, although there are many more. So the first type we're going to look at in this lesson is what is known as discrete geometry. So discrete geometry is the study of discrete points and discrete lines. Well, that's really helpful using discrete to define these things. So let's go a little bit further. Discrete geometry is when a point is described as a dot of some size, so the size can vary, and a line is made up of points that can have space in between them. So in discrete geometry, the description of a point is a dot. But our description of a line is a line of a set of dots in a row. So it no longer is drawn the way that we think of lines. It's sets of dots in a row that can have space in between them. They also can have endpoints. So in this case, we're going to look at example 1 to get this idea. So two discrete lines crossing in which the two lines do not share a common point. So we know in Euclidean geometry, where any two lines cross, they cross at a point. In discrete geometry, they could cross at a shared point if both lines hit that same point, or they could cross at the space in between the points or dots. So I drew it with a blue and purple line here, and they're just a set of dots in a row. Some size, so make them consistent in size as much as you can, and some space in between them. Again, you can kind of decide. It's discrete geometry. Now, you don't have to put arrows at the end of your lines. The reason I put arrows at the end here is because you could extend this as far as you want, or you could make this end wherever you wanted along this row. Same thing with the purple line. It's a set of dots of some size with some space in between them, and it can go on for as long as you decide in a row. These two lines intersect, but there is not a point that's shared between the blue and purple lines. They intersect at a blank space. So that's an example of two discrete lines crossing in which they do not share a common point. Now in our next problem, we're actually going to look at a little bit of history tied to Russia and a mathematician named Leonhard Euler. Now, I apologize for any mispronunciations throughout this. I'm definitely not a Russian aficionado or historian. So the Königsberg Bridge problem, through the city of Kaliningrad, Russia, flows the Pergola River. And in this part of the river are two islands. There are 7 bridges. So 7 bridges connected the islands to each other and to the shores. And it was common on Sundays for people to take walks over these bridges in the city of Kaliningrad, Russia. These walks and bridges led to a math problem. That problem is simply the question, can you walk over each bridge exactly once? So this was a common question that was posed in the Königsberg Bridge problem. So in the city of Kaliningrad, Russia, we know there are 2 islands in the middle of this river and 7 bridges total. The question is, could someone walk over each bridge exactly once? So they have to go over all the bridges and each bridge exactly once. So they cannot double back. So an example of this bridge setup is over here to the right. So what I'd like for you to do is pause the video here and take about 5 minutes or so and try to answer that question using this diagram. Try to figure out, can you walk over each bridge exactly once? And you can mark on this diagram, draw with pencil, whatever you need to, and try to answer that question. So you have to start, obviously, some point of land, can't start in water, and walk over each bridge exactly once. So pause the video, take some time to try to answer that. All right, so hopefully you actually paused the video, tried to answer that. If you didn't, then we're just moving on and you kind of skipped that purpose, but we'll move on to what ended up happening with this problem. So a great mathematician, Leonhard Euler, he's done quite a few different principles and ideas. He came up with maps and sketches in his attempt to solve this problem. So we kind of began with an overhead view like this. He then moved on to the idea similar to this diagram here in the middle, where he simplified it, the land masses, to smaller points here, and shifted a few things just to make it a more easier to visualize representation. So then that wasn't exactly where he wanted to go, and eventually it led him to creating a network that looked like this. So that idea of what Euler did, he thought of the land areas as individual points and the bridges as individual arcs connecting those points. The result is a network of points and arcs. So this result here, image 3 in this chain going down 1, 2, 3, this result is known as a network. The arcs can look like a straight line or they can be curved, connect our individual points, which represent our land masses A, B, C, and D here. So then, in this network, there is a path from any point to another point. Networks can also sometimes be called graphs. So this geometry of networks became known as the geometry of graph theory. So our first geometry we looked at was discrete geometry. Our second geometry we're looking at is graph theory. So in graph theory, it involves what's known as this diagram or a network. And in a network, the only points are the endpoints of arcs. So where an arc has an endpoint is the only spot where we can put points. These points have no size, even though we have to draw them as a dot. They have no size, and they are called nodes or vertices. Typically in graph theory, more commonly, they are called nodes. So we have arcs, which are all of our line segments, curved or straight, and nodes, which are our points or vertices. And the nodes are always endpoints of the arcs. So in graph theory, our description of a point is a node of a network. And then our description of a line is the arc connecting either two nodes or one node to itself. So a description of a line is an arc connecting two nodes or a node back to itself. So let's look at that. What they mean by that would be right here. One node connecting back to itself could look like a circle, could be a weird shape, a squiggly, whatever, as long as it ends back where it began. Then, this one here, nodes O and P, each have three arcs. There's this arc here, from O to P, there's this arc on top, and then there's this arc that looks more like a straight line segment there. So there's the nodes, O and P, and three different arcs. And then this diagram with Q, S, R, and T, we have four nodes, and each node has three arcs. If we look at this, S to Q, there's one arc connecting both. Q to R, well, where's the third arc that touches Q? It's this one that curves around from Q to T. So Q has 1, 2, 3 arcs. R has 1, 2, 3 arcs. T, 1, 2, 3. And S, 1, 2, 3. So 3 different examples here of different networks with different numbers of nodes and arcs. And the idea that we wanted to look at for going way back to our Königsberg Bridge problem is, can you walk over each bridge exactly once? Well, if we can trace a whole network exactly once without lifting a pencil, we call that a traversable network. So if you could trace over all the arcs in a network without lifting your pencil off the paper, it is traversable. So Euler started to notice that the number of arcs at each node gave a clue to whether or not a network was traversable. So Euler started to notice a pattern, and we'll look at that in just a second. So at this point, we know Euler took this Königsberg Bridge problem, kind of came up with this drawing here, this network, which in sense created graph theory. And then we have our nodes, which are landforms here, and the arcs, which are different bridges. So based on these patterns, Euler could tell us if networks were traversable or not. So before we look at example 2, I just want to skip down to what Euler's solution was. Euler's solution was that when a path goes through a node, it uses 2 arcs. One to the node and one away from it. Okay, that sounds like common sense. When a network has an odd node, a node with an odd number of arcs, so an odd number of arcs connected to that node, it must be the starting point or the finishing point for a traversable network. Then the next solution was, since a traversable network can only have one starting point and one finishing point, it turns out the Königsberg network is not traversable because all 4 of our nodes, looking back up here, A, B, C, and D, were odd, meaning they had an odd number of arcs touching them. D had 1, 2, 3. B had 1, 2, 3. A had 1, 2, 3, 4, 5. And C had 1, 2, 3. So, going back down, so in that case, we had 4 odd nodes. So that network was not traversable. You could not walk over each bridge only once. You had to double back at some point. So then our final solution was that whenever a network has more than 2 odd nodes, it will never be traversable. So if we ever have more than 2 odd nodes, that network is automatically not traversable. So what I tried to make more simple were just my notes down here. So taking Euler's solution, we can summarize that if a network in graph theory has 0 or 2 odd nodes, it is a traversable network. If we have 4, 5, 6, 7, or 8, and so on, so anything more than 2 odd nodes, it is not traversable. If there are 0 odd nodes, meaning all of our nodes are even, they have an even number of arcs touching them, that network is a special type of traversable one because you could start at any point and it would be traversable. If there's exactly 2 odd nodes, your path must start at an odd node. So now we're going to take those ideas and apply them to examples 2 and 3. So in example 2, it says for each of the networks below, they want us to first state the number of arcs at each node and then determine if the network is traversable. So again, our nodes are our points. So in this first example, it would be A, B, C, D, and E. And the arcs are the lines or segments or curves. So I wrote next to my different nodes how many arcs there are at each. So A has 2 arcs, E has 4, 1, 2, 3, 4, D has only 1, C has 2, and B has 3. So in that case, I have 1, 2 odd numbered nodes. So if I look at my rules, 0 or 2 odd numbered nodes, they're traversable. So that network would be traversable. If we didn't know the shortcut, we would have to try the different combinations of tracing with our pencils. In example 2, again, we have our different nodes, so I just went in and counted the number of arcs at each. F had 2, I had 2, G had 2, J had 4, H had 2. All even nodes. So 0 odd number of nodes, it's a traversable network. And then in example 3, going in and counting our arcs at each node, K had 3, N had 2, M had 3, P had 3, L had 3. I have 1, 2, 3, 4 odd numbered nodes, so definitely more than 2 odd numbered nodes. The network is not traversable. And then jumping down to example 3. So using Euler's rule to determine whether a network is traversable or not. So basically we want to know, does it have 0 or 2 odd nodes? If it doesn't, then it's not traversable. So again, I just wrote next to my nodes the number of arcs. So G, H, and K all had 2. F and J had 3. 2 odd numbers, 2 odd nodes, traversable network. And B, 1, 2, 3, 4 of my nodes ended up being odds, so it is not traversable. And in C, again, counting the arcs at each node, 3, 2, 3, and 2, 2 odd number nodes, so that network is traversable. So again, for today, the big concepts, graph theory, and if a network is traversable or not, you're mainly looking at these two bullet points here. And then, going way back to the beginning, we had discrete geometry, which the main idea can be summarized in this box here, where a point is a dot and a line is a set of dots in a row. So as you work on the practice problems, make sure you have your notes handy. And again, with the networks, take the time to carefully count the number of arcs at each node and use the shortcut from Euler's solution to figure out if they're traversable or not.